Hello guys, I'm back. So today today our lecture number will be 5, but as per the serial number what we have decided, it should be covering the fourth part of it. And this fourth part will be dealing with the factors which affect the performance of CMM and the sources of inaccuracies in CMM, like the ways in which these inaccuracies in CMM can seep in, or what are the conditions what you should take care so the accuracy is improved of CMM. Okay, so today's lecture will be having two parts. One will be your different sources of inaccuracies and some terms for which are used to quantify the measurements, fine, or to quantify the performance of the CMM. Terms for quantifying the performance. Now, I want to give some disclaimer today. That disclaimer, especially for this part, that these terms will be some test actually, like how these tests are done. And suppose if you want to ensure that the repeatability of a machine is good. So how to ensure that? So there will be some test. And how frequent, like how the test is done. If it is very simple, I can explain you. But if it is very complicated, especially out of scope of your study, I will not be talking about it. But still, the important points out of it, the crux, which can be asked in the objective of exam, that I will be just telling you in brief. Fine. So in this part, don't try to read too many books because this is very practical thing, and until unless you are not into the field, it will not be very much important for you. Okay, so these sources of inaccuracy in CMM are in general coming from three types. The first type is your temperature, then not temperature, I should say it as due to your environmental conditions. Environmental conditions. In this environmental condition, it can be your temperature, then it can be your dirt, it can be your vibrations. Okay, then second one is machine conditions. And last one is your operating conditions. So these one by one we will take up. Fine. So the first one is your environmental conditions. So in environmental conditions, as I have just mentioned in here, that first one is your temperature. So you can very well understand that your CMM heads, the tool post or the probing head post, which moves on the rail, all the dimensions are a function of time. With time, the length changes, and you must be knowing that delta L is equal to L naught 1 plus alpha delta T. This is the thermal strain. Change in length is equal to L naught initial length 1 plus alpha, which is the thermal expansion coefficient, and delta T is the temperature change. So this is your change in length due to temperature. So if your measurements are done at different temperatures, so the entire scale or the entire CMM structure will expand, or it will have different change in length, and you can understand that the repeatability of your measurement will not be there. Suppose if you are doing some measurement in November when the winter is there, and when you are doing the same measurement in summer, so the data what you will obtain will not be very much relatable to each other, and there will be some deviation. So to maintain this, a proper care has to be taken, and that is that entire CMM is placed in a thermal controlled, temperature controlled environment. Now this as per standard it is 25 degrees centigrade, So you're like 22 to 25 degrees centigrade is the range. So wherever the CMM, all the measurements are done, the place, like the company or the place where this is kept, they will be ensuring that the temperature inside be in the range of 20 to 25 degrees centigrade. So it will be low, like whether that whatever be the season, but the temperature inside the room where the CMM is placed will be in this zone only. Fine. So this will ensure that the temperature is the thermal strains are under check. Now, I am saying that this temperature controlled environment, but it is not so easy also, because the temperature is not a problem. The main problem is temperature gradient. Temperature gradient is the main trouble. So sometime it might happen that, suppose if this is your room, you are placing your CMM over here, and your AC is centralized. If not centralized, it is having port from here. So this portion will be very cold, and this portion will not be so cold. So there will be uneven expansion in the machine itself, and that may cause another sort of deviation. Fine. So there has to be a cooling system which will ensure that the thermal gradient in the room is under check, and that thermal gradient is again like given to you by the manufacturer. This thermal gradient will be like for a suitable uncertainty level or the deviation level. A manufacturer will provide you this data, and you have to maintain that temperature gradient within this room. Not only the temperature, but the temperature gradient has to be checked. Fine. You cannot have a fan over here, because if this fan will be there, then there will be pressure shocks coming, and these pressure shocks may again just disturb the probing head. The probe head is very sensitive; it will start vibrating with this air. So again, the captured data by this probe head will not be very exact. So there are many small things which has to be taken care, and so a very controlled environment is maintained. Fine. Then similarly, the second one is your dirt. Just imagine like your head, like this is your granite slab on which the jobs are kept, and here is your probing head, and this probing head is moving on some sliders. Okay, so now these dirts are coming and accumulating on the sliders. So do you think this movement will be smooth? Of course not. So if there will be vibration along its movement, probe head will move. And suppose by machine system you will say that please this you will be feeding some data that this post should move by suppose some 10 centimeter. Because of this dirt, it might not move 10 centimeter. It will just move 9.1 or 9.99. So this 0.01 mm deviation will be there just because of this dirt, which has not allowed the movement of this system, this particular thing. So this point one, and then there will be some uncertainty in the measurement. So you can see this is the minimum error which will come, seep in. So these dirts will cause too much trouble. But now, suppose if sometime if you will go to an industry, you will see this CMM placed just next to the manufacturing house, like the place where the manufacturing is happening. Just next to it, the CMM is kept, and then there you cannot control dirt so happily. So then there you have to adjust with the poor or some amount of deviation which will come, and then you have to do the trade-off between the accuracy and the portability. Fine, because every time it will not be so convenient to pick the job and then go to some far place where it is completely isolated from vibration or dirt, specifically to a CMM facility or dimensional inspection facility where you will be doing the checks, bringing it back to machining for corrections. It is not always possible. So what they do, just to save time and transport, they will be making, this is the machine shop. So just close to machine shop or inside the machine shop only, they will be putting the CMM. So very quickly measurements be done. If there is some corrections, it can again be sent to the machine shop. Again, some corrections actions are done, sent back to the machining measurement. So just for that sake, it is kept very near. But again, in that case, the vibration in all the machine shop machines will create disturbance in the CMM. All the temperature you cannot maintain. Suppose here welding is happening, You cannot ensure that that temperature gradient is maintained for the CMM. That will not be possible. So of course there will be some deviations in the measurement which you have to adjust with. Okay. The third one is very basic, that is vibrations. Vibration is a very big trouble for this machine, and this vibration is not only by nearby machine. Suppose if this is CMM and here I start drilling, so you can understand that this vibration will travel through ground, and then this they will disturb this table you say, or the ceramic platform which is there. This particular platform will start shaking. So if the job on this will also start shaking, so the measurements captured by the probe will not be very good. So this vibration is not only because of this. This vibration can also come because of acoustic pressure, and this acoustic pressure can be due to many regions. Suppose there is some, like I'm just talking about how sensitive this machine is, that it is even getting affected by the acoustic pressure. The acoustic pressure means if there is some uh, vibration, rarefaction and compaction in the air because of uneven pressure, then also the probe will move and then the disturbance will come, and this will not give you a very exact result. So when it is so sensitive, then you can of course understand the drilling or milling on nearby machines vibration which is coming, means vibration isolation, how important that will be for this particular machine, that you can understand. Okay, so these were your environmental environmental conditions. Now we will talk about machine conditions. Now in machine conditions, what happened, this machine conditions means, right, machine conditions. This machine condition generally occurs due to deviation in machine coordinate system, what has been defined, or which is the ideal one, and which has deviated from this. Fine. Like suppose if you have designed the machine like this, I am making the cantilever type. Fine. This is the column on which your probing is there, and then you are keeping some job over here. Okay, and then you are taking the measurements of this. So this is your head. Fine. So there, if like last class also I was talking about this. Suppose if you are keeping this more than the rated weight, if this machine is rated for 100 kg and you are placing a job of 200 kg, then what will happen? Then there will be deformation in this structure. Deformation in structure, and this deformation in structure will cause improper measurements. Okay, or if there is some like you are using this machine from years, and due to the weight of this entire probing system, if this thing just slants a little bit, then also you can understand there will be some error. Now, of course, this deviation you cannot see very apparently, and this error will be just seeping in into your measurements. So, this type of machine conditions, poor machine conditions, which results in poor dimension inspection, has to be checked, and these are done by AMCs. AMCs or machines. AMC means annual maintenance check. So a company person will come, and you will be having some contract with the company person. Like suppose you have one AMC for 1 year. In 1 year AMC, there will be some preventive measures and some breakdown maintenance. So in preventive maintenance, suppose you have two preventive maintenance in 1 year, then every six months, a person from company will come, and he will bring all sort of his own equipments, and he will measure that how much deviations has come, whether any deviations has come or not, whether there has been any permanent deformation in the structure. So if so, then these preventive maintenance will check those things and they will report you back that, sir, this machine has become hunched and you need to change this particular thing, and there will be some amount of money what you will have to spend, but you will be getting perfect dimensions. Or suppose if this deformation is permanent, then they can adjust it also automatically. And those, like, because finally these data has to go to a computer, right? So if you know that these are very systematic error which is coming in, you can adjust in this computer, like, okay, fine, you know that 1 mm deviation will always come. So if your 10 mm is coming, you know that 1 mm is already a part of it, so exactly 9 mm or 11 mm. Fine. So these systematic errors, if it is systematic, then it can be taken care by the automatic corrections, and but that has to be told to you, and those will be told to you by the company people who will come after some time, or come in preventive maintenance, and they will do this breakdown maintenance. Is suppose if in between your machine breakdown, then the company person will come and correct it up for free of charge. It is not it is just little bit different than warranty what you have. Okay, in warranty, what happens is if suppose some part stop working or some part is not working at all, then those people will come and then they will change it free of cost. But in AMC, for very high value machines, we take AMCs. In this annual maintenance check, they will come, they will gauge the performance of the machine, and whether if it is suitable, then it's good. If not, then they will just take care of it. Okay. Now in this machine conditions inaccuracy, there is something called as apps offset. Okay. So what is this? Now this is a type of positional deviation. Now it is the perpendicular distance between the measuring line and the measuring system. Suppose you want to measure, you know that this is the correct direction what initially you have set in the machine coordinate system. But over the use of it, now there has been a change in it, and now this is the measuring line. So you can see that there is a perpendicular distance between them, and this is a sort of error. I mean that when your machine was sliding and the probe has to move along this line. Okay, this is the probe line. But due to some hunching or because of some deformation of the structure, now probe is not moving along this line, but it is moving along this line. Okay, so this is the error, and this is what I was telling that this error can be adjusted automatically. Automatically, you can adjust this. Adjust this. So this particular deviation, the perpendicular distance between them, between the your measuring system and the measuring line. This is the measuring line, and this is the direction measuring system. Measuring system. So the perpendicular distance between this is called as Abe's offset. This can be corrected by arithmetic corrections, or these arithmetic corrections, arithmetic corrections are also called as CAA, and CAA stands for Computer Aided Accuracy. So if someone is asking how what is Abe offset, you know it is the perpendicular distance. Can it be corrected? Yes, by arithmetic corrections, and these arithmetic corrections sometimes in technical language it is also called as CAA, Computer Aided Accuracy, and these are done by laser interferometers. Okay, now laser interferometers are used to determine this offset, and then those data are put into the system, and that is also known as arithmetic corrections or CAA. Okay, now please don't ask me what is laser interferometer or how they work, because in metrology you might have studied about this, and if not, then you better study about this, because it is a very common type of instrument which will be used again and again. Fine. So it is always better to know about this. It uses some principle of lights. You will just read about it. Okay. Now in machine condition, there can be something because of probe deflections also. Now in machine conditions, due to probe deflection also can cause error. Now what do you mean by probe deflection? Suppose you have a job of this sort. Okay, this is your job. This is your overtime. Fine. Now you have a probe of this sort. This is the ruby tip. This is a stylus, and this is the probe head, and then this has to move, and this has to contact this point for the measurement. Okay. Now what do you think what will happen? When this probe will come over here, after this, when if it will move, there will be a deflection in the probe. It will become something like this. Okay, so such probe deflection, I have just exaggerated the view, but you can understand that it can happen. Suppose if there is some internal dimension which has to be measured, and you are putting a probe inside thinking that there is another surface, you can understand that it will touch any other surface and there will be some deflection in the stylus, and the measurement what will be taken will not be very correct. So such probe deflection or the probe stylus deflection due to the contour of job cannot at all be eliminated, and if it is happening then some error will seep in. Fine, so these are some machine conditions. Now let's talk about operation specific factors. The third one is operation specific problems. Now what are these operation specific problems? This you have, like, when you will understand the type of troubles what people face in CMM machine, then you will think why we are using this system on the very first place. Now I will tell you. Suppose I told you that we use air bearings for movement. Okay, we use this. I discussed in the last class that we use air bearing. Now in air bearing, you need some pressurized air. Okay. Now what can happen? There are many troubles. Suppose this pressurized air, your voltage is fluctuating. Voltage of electricity is fluctuating. So if this voltage is fluctuating, then it means then the supply of this air will also fluctuate. If the supply of air will fluctuate, then this pressure will fluctuate. If this pressure of air will fluctuate, then the air bearing, whatever the air cushion what you are forming, that will also fluctuate. If that is fluctuating, then finally the air bearing, like the bridge type here was air bearing, in between there was the your platform, and on top, from top, probing system was done. Okay, so this here was the air bearing. So, and this movement was very smooth because of this air bearing. So now I am talking that if your electricity voltage is varying, then the pressure will vary. Pressure will vary, then the air at this point cushion will vary, and this movement will not be smooth. So the vibration will come, and then the trouble will come. Understood? Now, second trouble. Suppose this air, whatever you are pumping in by the compressor, because of some reason that compressor air, whatever is coming in, is high in humidity. So because of this high humidity, what will happen? Now, this thing is your. Can you tell me what is this material? I discussed in last class. This is granite. Now, this granite, in presence of humidity, will swell up, and that swelling up of granite will cause the change in dimension, and then the change in dimension will again cause the change in like the difference in measurement. Okay, so this air, whatever is being pumped in, has to be dehumidified before it is being transmitted. Okay, now such type of things are also there. Then what else? Now, one thing is called as mass of workpiece. Fine, you can very well understand that the mass of workpiece can cause the deformation in your uh, structure itself. So the problem will come. Then there can be uh, deviation in measurement due to your deformation in job itself. Deviation due to deformation of job. What do I mean by this? That suppose this is your probing system and you have a very soft type of material. This is your job. Okay. So when this probe will touch this, there will be a deformation in the job. Okay. Now this deformation will cause poor measurement. Understood? So this deviation or the deviation, this is deformation of job. And this deformation will happen because the stress will be very high. So for very soft or jobs, like the jobs which are very highly prone to get deformed, we don't use contact type of probes, then we go for the non-contact. But there is another problem with non-contact, that in non-contact probes, the entire accuracy of your measurement will depend on the 3D cameras. And these 3D cameras are not very much giving you the correct result. Although this is very fast, but still the measurements are not very accurate. Fine. So that is one another trouble we often face. Fine. So with this, then one more is there that should also I tell you, because of poor size of probes, probe tip. Now, what do I mean by this? It's better if I show you a diagram for this. Then you will understand it in a better way. Just let me look for one. I think I have one. Yes. See, now, yes. Now you please see in this. This is the contour of your job. This is the contour of your job. Contour of job. Okay. This particular, like this hills. Now suppose if I use this particular size of your probe tip. This is probe tip. Then this particular will touch this job at this point and this point. Okay. And then there will be your radius compensation. I believe you remember this in the last class. At last we discussed about this, and like the cosine error was also coming from this. Okay, if not, kindly refer to it. Fine. So these are the cosine, like the direction compensation or the radius compensation, what will be done. So at this point and this point the radius compensation will be done. So you can understand that from here and here 2 points are being detected by the probe. So the data what will be received by the machine will suggest it that the curvature or the contour of the job is from here to here only directly. It will not talk about this point. If this will be the probe tip you choose, this is too big, too big. Okay. Now, if you are not choosing that and somewhere you are choosing the below one, so the below one will touch at one point and all the points very nicely, and you can get a very smooth type of curve. So now a question can be asked. This is the smaller probe tip. So from here, accuracy is good. But you can very well understand that there will be so many points that this small probe has to touch to get the entire form of the object. Whereas for probe tip, if it is big, then less number of points will be touched and you can get the form of the object. But then you are adjusting with the accuracy. So which one should you choose? The larger one or the smaller one? So in general, people tend to say the smaller one. That its our accuracy is very important when we are doing dimension inspection. Then our aim is to obtain the deviations or the very exact dimensions, but it is not true. Means it is partially true that we use smaller probes, but we try to optimize the size and we try to maximize the size, because when the probe size will be bigger, then you will touch at less number of points and the data what you will obtain, that will have less computational space. Okay, so in that the like in computer you might have studied about complexity, time complexity, which is given as big O notation, small o notations. So this reduces your time complexity and space complexity, whereas smaller probes, they increases your time complexity and space complexity but increases the accuracy. Fine, so always we try to select the largest probe without compromising the accuracy. So in this case, this is the thing, but going below this will not be good. Going bigger than this is again not good. So this is the optimum size of the probe what we will be using in here. So we have to always optimize the probe tip dia. Okay, so that is one thing. Now with this, our three reasons from where the inaccuracy in CMM can come finishes. What were the three? Now I'll just brief it up. There were three reasons. One was environmental, second one was your machine related, and third one was due to operation. So in this was in this dirt, temperature, etc. were there. In this, one important thing was Abe's offset. This is the named one, so I'm just telling it is important. And then the operation, you saw how fluctuation of electricity or the poor size of probe, all those troubles were coming. Okay, poor probe. So with, by the way, with probe there are two things till now what I have discussed. One was your cosine error, which was discussed in the last class, and then now is coming due to size of probe. Okay, size of probe. So with this, you understand the like the reasons from which causes inaccuracy. Fine. Now there will be something which is called as performance evaluation of CMM. Now, what is that performance evaluation of CMM? Performance evaluation of CMM. Okay. Now, see, whenever suppose some person is coming and he is claiming the might of CMM, then they have to justify that my CMM is so good. Like, if someone is claiming that he's like, when I say someone, I mean if some manufacturer is claiming that is claiming the might of CMM, then they have to justify it. Okay. Now to justify this, there are standards. Now standards like you must have like heard of this benchmarking, a gold standard. So those are some standards. So which if a machine is matching to it, then we say it is very good machine, or if it is not matching to it, we say it is not so bad machine. So our aim will be to judge the performance or how to do this performance evaluation of a machine. Fine. So now in doing so, there are some issues what most of the manufacturing people face. And those issues you should know. Why you should know? Because then it will give you a better judgment while marking the answers and also to understand what is happening. Okay. Now, the biggest problem with with the metrology people are, suppose if I say you give me 1 meter, right now I'm just discussing about the problems. Problems with metrology. Okay. Now this problem, what I will tell you. Suppose I ask you to make you 1 meter long rod. If this is my need, okay, you try to do this. First problem you will face that you will not be able to manufacture exact 1 meter length. Not able to manufacture. And second trouble, what I will feel that suppose if you give me some length, I cannot measure it exactly that this is 1 meter exact or not. Are you getting my point? Like first trouble is in manufacturing that how will you ensure that this is 1 meter exact length? And second one, how will I confirm that you are correct or wrong? You are trying to cheat me or not? How will I know that? I don't have no way to verify it. So the business of accuracy is very difficult. First problem is the difficulty in manufacturing. If I say 1 meter rod exact, there has to be no, not even 1.001. It has to be perfect one. So first thing is the trouble will be you cannot make it exact like that. And suppose if you give me some length and you ask me, sir, it is perfect 1 meter, you verify it, I cannot do that. Fine. This is one trouble. So then there is a tug of war between manufacturers and the users. Now we have to buy machine. Suppose you are in a aerospace business and your aerospace business, all the components what you make, they have very tight tolerance. Okay. Now to qualify these tight tolerance, you need to have a very accurate machine. This is your need again. So this accurate machine, you cannot make it. You will try to buy it from market. So in market, there will be manufacturer. And this manufacturer will say that he has a machine. This is manufacturer's claim that I have a machine which is very good and it can measure with like my accuracy and repeatability is very good. He will give you some numbers for it. And then your aim will be to buy this machine. Now he is claiming it. And you have to prove that these claims are good or not because your need is already present because your jobs are already in pipeline. So you have to buy this machine, prove your qualify your objects, and then you have to use it. So this is from the user side problem. Okay, so user side has a trouble, manufacturer has the trouble. Manufacturer has to sell you the machine. So now what will happen? Suppose you will order one CMM. You will say that, see, I want a CMM whose tolerance is zero point 0.1 micron. Okay, like I want a machine who can even measure zero point 0.1 micron. And these people will say that, okay, you give me a job of zero point 0.1 micron and I will measure it. So there will be a tug of war between these both people. Understood? So finally, what happens is they both will have some target. Manufacturer, what they will do, they will try to guarantee the uncertainty. Suppose they will suppose manufacturer's aim will be, now manufacturer will also not try to cheat you. Okay, they will also try to give you the best of machine and best of product. So his name in market is maintained. So what his aim will be? His aim will be to manage the claimed uncertainty. What this fellow will do, he will say that, see, my machine will always be like, it will have an uncertainty of plus minus 0.5 micron. Like I cannot remove it. He will say so. Like suppose if my machine is telling you 1 meter, it can be 1 meter plus zero point 0.5 micron or 1 meter minus zero point 0.5 micron. So this zero point 0.5 micron uncertainty is there in my machine. This what he will try, and he will try his best to maintain this claim. This will be the aim and claim of manufacturer, what he will try to meet. And user expectation will be that whatever be the means whatever be the uncertainty what he's trying, it should be well within his acceptable limits. Okay, like the measurement range, his expectation will be that the measurement range should be in the prescribed zone. Means suppose if he will take the worst case scenario, he will say that if I am giving him 1 meter and his machine is giving me 1 meter plus or minus zero point 0.5 micron, then whatever be my need, it should be well within this. Understood? That this will be the he user's need, that he will try that this uncertainty is well within his acceptable limits. That will be his expectations and his need. And with this adjustment between these two, they will be buying any sort of machine. So these, so in again, I will brief it up. What I want to say, that there are two parties. One is user, another one is manufacturer. Manufacturer aim is to maintain the claimed uncertainty. Okay, and user aim will be to check that the claimed uncertainty is well within the acceptable limit of his product's spec. Okay, and in between these two, the adjustment in between these two is taken care by, which is called like, this is also called as golden rule of metrology. Like, this is not important at all for the gate perspective, but this can be asked in ESC, or it can be asked in your sometime in interviews. Like if they go very gaga on you, so they might ask you, what is the golden rule of metrology? And the golden rule of metrology is that the measuring uncertainty should be 10 times smaller, should be 10 times smaller than the manufacturing tolerance. This is your manufacturing tolerance, and this is your this is your uncertainty, and this is the manufacturing tolerance. So your measuring uncertainty should be 10 times smaller than the manufacturing tolerance, and this is also called as golden rule of metrology. So now this measuring uncertainty can come because of many reasons. These measuring uncertainties can be coming due to your systematic error, or due to your random error, So this systematic error again can be corrected by your CAA, because systematic error means you know from where these errors are coming. You know the reason of it. So once if you know the reason, you can correct them, and you can correct them automatically, and that is again called as CAA, computer aided accuracy. So that this can correct this. This random error, it cannot be corrected. You have no option for it. So this will always come and you cannot correct it, and because of this only this uncertainty some 10 times factor is taken. Okay, so that is the point. Now there are some what you say, some type of test to quantify machine performance. Okay, now there are some type of tests, some types of tests to quantify machine performance. Now in this, I will be just telling you the name. I will be telling you like how that quantification is done, and then I will tell you. I will be very brief in this. Okay, I will not try to pull this up because if to explain this in detail, it will take like it will fall out of the scope. Okay, so I will just try to keep it as short as possible with all important points. Now, first one is hysteresis test. Now, in hysteresis test, this is uh, very important for your touch trigger type of probes. Touch trigger types of probe. Now, I am very much sure that you people must have studied sometime in your lifetime such type of curve, the hysteresis curve. Okay. Now, this test is not related to this one in any way, but it is depending on repeatability of the data what has been obtained. Okay. Now, if you remember the touch trigger, what I discussed in last class, it falls under the category of contact probe. And the advantage of this touch trigger was that the pressure was always maintained. Pressure was maintained. Okay. So I feel it will be better if I explain this a little bit more in detail, because if I will not do it, then no one else will help you in understanding it. So it's better. I feel I should do the justice with this. Okay. Now this is your touch trigger. See, till now I have just told you that the pressure was maintained, and this pressure was maintained, and especially in the case where the directions of this measurement was changed, in those cases also the pressure was maintained. Okay. Now how is that done? Now in this will be your probe. This will be your probe stylus and probe head, and then we will put one sort of flexible parallelogram. Flexible parallelogram will act like a spring. Okay, for your understanding, you understand it like a spring. So when the probe will come in contact with a job, then the original axis is this, and there will be some deviation in this flexible parallelogram, and this deviation, whatever is happening, that will be taken care by the sensors, and when this deviation will happen to a limit, then that limit will be taken as pressure. Like for same pressure, these deviations will be same, and these deviations when they will be like up to some value, what will be set by machine, this will just lift it up. Okay, so this is how they maintain the pressure at this point. Now you can understand with numerous readings taken at this point, this point, this point, and this point, all the points, and be the same probe being used hundred of times, you can understand this elasticity or this flexible parallelogram will reduce, and sometime it may happen that this is not coming back to its original axis. This is its original axis, this is its original axis. So sometime it may happen that it is not returning back to the original axis. So That is called hysteresis in displays. Okay, so any distortion which is permanent in nature and is causing any trouble in this pressure sensing is called hysteresis. Okay, so any test which can qualify this is called hysteresis test, and it is done by means taking multiple readings. Okay, so yeah, and fine. So this is one thing. Uh, Now, I should go to another one. Like, I just wanted to tell you what is hysteresis test. So this hysteresis test is done for this thing. Hmm. Then second one is your linear displacement accuracy test. Second one is your linear displacement accuracy test. Now, this is to test your machine coordinate moving system. Okay. Suppose you are giving some data in your computer that will move the probe column on this head. Okay, so whatever data you are giving, suppose you are giving that please move 100 centimeter along y-axis. So whether this particular machine is moving in y direction by 100 centimeter or not, that has to be tested, and those are called as linear displacement accuracy test. Now it provides a traceability to the international standard of length and is done by either laser interferometer or step gauges. Okay, so this is done by your laser interferometer or step gauges. Okay, and this will have its with like internationally whatever you have given the measurement of length as 1 meter, so it will try to establish a correlation with that. Okay, then your third one is your repeatability test. Repeatability test. So in this, it is done by taking multiple readings of the same thing and then check whether the readings are coming same or not. Means repeated measurements are taken and compared. Okay, now when I say repeated measurements, a very normal question will be asked. Like it is not so normal. You might not understand the seriousness of this, but I will just like try to put a force on this. That repeated measurements of what? Can it be a plate that we will take many readings on this plate? No. Generally, we go for spheres. Now, of course, you will ask me why spheres? Why not something else? Now, spheres are used to do multiple readings. What we do, we take some. I will tell you. We will take some sphere. We will take some sphere, okay, and then we will fix this, mount this on a pedestal, and then we will try to take multiple readings of this head. We'll move the machine here, test it, again take it to some other point, then again come back, try to test the tip of this, again go back, again try to test it, and we will do multiple number of times reading we will take, and we will see whether the same reading is repeating or not. If the same reading is coming 95% of time, then we say, okay, fine, this is qualified. Fine. Now, why do we take sphere? Now, this sphere is taken because this is a sphere we take, or we take rings, because these are some objects which is having some known curvature. Okay. So, in actual jobs, when we will suppose if this is my actual job and you will be doing the testing with probes, then there will be deviation in direction. Okay, you can see this probe direction is changing. So to take care of this directional nature of the probe, we take a object with known curvature, and then we do the testing. So by that, at least we will know that okay, with this curvature, you are getting the repeatability of this much. If there is some unknown curvature, then it's different. Fine. So that's why multiple readings. We take multiple readings, and then these readings are taken on a sphere or rings only. Okay. Then there is something called as volumetric performance test. Volumetric performance test. This is also called as ball bar test. Okay. Now, in this, it determines the machine ability to allow consistent measurements of an uncalibrated length in various specified positions within the working zone. And it gives the accuracy in length and working tolerance. It is done with a prismatic bar having two spheres at both the ends. Fine. This will be one length. Okay. This is this is ball bar. These two are ball and this is the bar. So what we do, we take again, these two balls are there with known curvature. So we will take the measurements over here at different locations. So, means this is curve. Fine. This is curve. So at this point, suppose one measurement is taken at this point is taken. So on, suppose you are taking here, then you are taking here. So what you are doing, that you are just there is some uncalibrated length, and in different various specified positions within the working zone, you are taking the measurements. Okay, so it allows for a consistent measurements. Fine. Then it is done using ball bar. Fine. This is the point you have to understand. Then there is something called as bidirectional length measurement. Bidirectional length measurement. Now, what do you mean by bidirectional? Now, bidirectional means, suppose you need to measure length along a straight line, then you can measure it very happily. This straight line, and this distance can be measured. Okay, but suppose if this distance is measured on a sphere, then you have to. It is not, first of all, it is not linear. It is along a curve. Okay, this is along a curve. So along a curve, two things changes. First, the direction also changes. Direction changes, and then you progress in space. Progress in space. So there are two parameters which changes. Fine. One is increment in length, which happens, which is progression in space, and then there is change in direction. So such bidirectional length measurements are to be done. Okay. Now uh, it is done by gauge blocks. Okay. It is done by gauge blocks. This is important. Like suppose someone can ask you how bidirectional length measurements are done. It is done by gauge blocks. Don't confuse with this sphere right now. I just drew this sphere to make you understand how bidirectional lengths are coming. Okay. And it is sometimes also done by using three spheres. Not one, but three spheres. Gauge blocks, or using three spheres in different configuration. Okay, so there will be some three spheres, and they will be at different locations at different height in the space, and different locations. You can understand all these are in same plane. Okay, so different heights are there, different configurations are, and probe will come touch at different things, and then they will have an idea of bidirectional length measurements. Okay, then something of called as positional accuracy. Okay, so positional accuracy. So this positional accuracy means it is the ability to move and return to a specified position within the working range. It is very simple. Fine. It is very simple means it is the ability of a machine to go to some distance and come back to the same distance back. Okay. To move and return to the specified position within the working range. Whatever be the working range, you just have to go back and forth into it and just see whether it is coming to the same position or not. Then some terms is called as straightness. Now straightness you can understand, like this is very similar to what I was telling you in apes offset, that the machine direction, I say go in this direction to the probe. Now whether it is going in the straight line or not, that is called as straightness. Okay, then there is something called as squareness. Squareness. Now squareness means your probe will measure two directions in two perpendicular directions. Okay, the measurements will be done in two perpendicular directions, and then it will be seeing whether it is 90 degree or not. Okay, so it actually checks the angular deviation, deviation of two perpendicular lines. Fine, directed axis along the square. Okay, now there is something. Yes, now very important. I was missing. I just remembered it. It is your error due to rotary motion. This is important. Why it is important? That this was your granite bed, okay, and this I was telling is your probe. Okay, I draw this CMM only because it is very easy for me to draw. Fine, but it is true for all other CMM also. Please take a note of it. And this head was moving on this channel. Okay, so when this post moves along this, then there can be different types of error, and those error I will show you by diagram. Please wait. These error are, see, now this is the base of your column. Okay, this is your channel, this is your channel, this particular thing is your channel, and this on over top of this only your that column is there. I guess you can understand column. Hmm. So when this slides over this is your transversing direction. Okay, this is sliding on this rails here. This is the y-axis, then z-axis, along with tool and x-axis. Okay. Now, when this post will move, there can be three problems, three type of rolls. What can happen? Yawing, pitching, rolling. Yawing, yaw, pitch, roll. And because of these angular deviations and the inertia of the column post, there can be some deviations. Fine. So you have to take care of these things. Means question can come, what can be the error which can seep in due to poor rotary movement of column or rotary movement of your tool post. So roll, pitch, yaw, all the three are the type of, these three things can cause the trouble. Okay. Now the working tolerance for any rotary axis. Now for any working tolerance for any rotary axis are specified by two characteristics. Are specified by two characteristics, and both the characteristics are, you just remember the name because this name can be asked. One is 4-axis working tolerance, and another one is called 3D alpha working tolerance. Now these are two characteristics which make the working tolerance for any rotary axis. Now at this point I will try to make one point, that if someone is asking you how many axes are there in CMM, so there are CMM with 5 axes also. Okay, so you don't get confused between this 5 axis CMM and your 4 axis working tolerance for any rotary axis. Okay, this is the working tolerance of rotary axis. So please don't get between 4 axis and 5 axis. In options they can put like this, and what is the working tolerance of any rotary axis, and then there will be option as 2 axis, 3 axis, 4 axis, 5 axis. And somewhere in book or in somewhere in note you might read about this 5 axis CMM, you will get confused, you will mark it, which is not true. This is 4 axis working tolerance. Okay, and this second one is your 3D alpha. Okay, now there are some uncertainty related to probes also. Now, by the way, in probes there are many uncertainties. Uncertainties related to probe. I will just recap one by all the problems with probe. Number one was your direction and cosine error we discussed in last class. Then second one was your deflection, probe stylus deflection, today's class. Then third one was your poor size of probe, means if it's smaller then too much data, if bigger then like improper form. Okay, and the final one today, the final one what will be, there can be probe uncertainties in one probing 1D. Like these uncertainties of probes are actually classified into three things: 1D, 2D, and 3D. Now, this 2D and 3D is not this same 1D, 2D, 3D of your coordinate geometry, or it is nothing has to do with your dimensions, but it is just classified like this. And I will not be going into details in this, and I will just tell you how they are measured. These are measured using gauge blocks or gap gauges. Gauge blocks or gap gauges. This 2D are done, 2D uncertainties are checked by ring gauges. Ring gauges actually, see this GAUG is called gauge, but somehow we end up saying it gauge. Okay, but correct pronunciation is gauge only. And these 3D uncertainty of things are done by spheres. So with this it finishes. Okay, all the uncertainty whatever I have just said. With this, it finishes. So just I will going into the last part of it, which is the fifth part of CMM, which I was talking about evolution of CMM. Now, this evolution of CMM means what after CMM? What after CMM? So, is the CMM our final resort? No, it is not so. CMM, the biggest thing in CMM is that it will give you the outer form. Outer form can only be given. Now, some people say that CMM help them in your reverse engineering. Okay, which is not completely true. Because suppose if there is a mouse, means your gaming mouse. Okay, this is your mouse. Hmm. And this gaming mouse has to be reverse engineered. Do you think if only outer form is given to you, can you make this mouse? No. So this is not entirely used in reverse engineering. In only it will give you the outer shape. To know about the inner things, you need to have a very advanced technology. And that advanced technology, what we use nowadays, is called CT system. And the CT system is, the CT stands for computed tomography. And this this CT system and what you get done for your CT scan, they both are same. CT scan for head, what you get, or medically what you get tested for CT scan, and the CT system what we use in industry, both of them are same. That is the thing. Only the energy source what we use are different. So in computed tomography, I will just be briefing you out very quickly. What we do, we use a source, X-ray source. We will use a X-ray source. With this, we throw the lights on an object. Suppose your gaming mouse only. Okay, this is the mouse. So we and this we will keep on a pedestal. This pedestal can rotate. So this mouse will keep on rotating about its axis, and here will be one digital screen. So all the images will be captured on it, and by software we will reconstruct them, and then we will say like what all materials are inside wiring. Everything can be seen. If you are interested, you can go for go on YouTube and check for your CT industrial CT systems. You can see there will be hand grenades what people have reverse engineered. There are many things what people have reverse engineered, like your hand watches. There will be many super images on internet which you can happily see. So if you are getting the internal know-how also with your CT system, then you can understand that it will give you a very good measurement of internal dimensions also. Good internal dimensions, which your CMM is not giving. Okay. Also, CMM is not completely used for your reverse engineering. CT systems are used because if you want to reverse engineer some material, then you will have to break it, then you have to test it by CMM part by part. Whereas with CT system, without destroying the object, also you can see. So this CT system is the next step on CMM. Like it is better system than CMM. Another evolution means what can be improved in CMM is your data acquisition speed. Like in chapter 2 or 3, I might have discussed about analog scanning. So in analog scanning, too much data is coming into the processor, and we try to if somehow we can process those data very quickly with computing speeds, then it will be a very good system. Then all the improvement what we can do in CMM are related to your these things only. Either computing power you have to improve, or you have to improve your internal dimensions, or you can improve your non-contact proving systems. Okay. because as I discussed, if the material of measurement, your job is very soft, then your contact probes will not give you very accurate result. And in those cases, non-contact probes are only alternative. And in non-contact, the accuracy reduces. So if you are doing some advancements in your image capturing methodologies, then that will be a very good move. Fine. So this is the evolution. And with this, I am finishing the entire CMM portion. Now, one more lecture I might take, and that will be the epilogue, where I will be briefing up all whatever we have discussed in the last 5 lectures. Fine. So with this, thank you for listening me out. Kaatil Kabootar signing off. You can always, like, if you wish to hear me more about different other topics, kindly like, share, and subscribe, because as I have discussed in the very first lecture, that you can only increase the area in the curve as I have discussed. Fine, kindly see my first lecture last few minutes. You will understand. You try to move this up. I will try to increase this content. Fine. Other than that, everything is fine. Thank you for listening me out. So, bye bye. Jai Hind.